In this video, we're going to take the NIR data that we've been exploring over the past several videos to now build a regression model with it. So in the previous videos, we've done exploratory data analysis. We've looked at this in a number of ways visually. We've built a classification model to predict whether we have authentic material or adulterated material. And now we're going to take those adulterated samples and build a regression model to estimate how much the materials have been adulterated. Let's get started. So I've got a notebook here where we're going to begin with our usual imports. And I should say, by the time you see this video, the data is also in a GitHub repository. So here you can see how I've quickly created our process data, but I'm going to just read from my process data folder. And for you, you can just use this pd.readcsv and then the link in that description to access the data. And I'm going to, instead of using the classification data set, I'm going to use my percent adulterated data set for this regression. I'm going to run this cell here and then these next several cells so that you can see what this data looks like. So here we have all the wavelengths in this NIR range that was collected on this device, as well as the first 5 rows of our data. Instead of head, if I use sample and just select 5 random rows, you can see that we have 50% adulterated, 90% adulterated, 10%. And so from the very beginning, I'm going to begin by scaling all of my X data using the standard normal variate. And now I'm showing you the first 5 rows of that. We don't need to touch the Y data, of course. We're just going to focus on the analytical data on this side. And instead of using a support vector regression, analogous to what we've been doing for our classification, I want to just use a ridge model, a ridge regression model, which allows us to regularize this data. I challenge you to apply a different model, and maybe I'll feature that in one of my future videos. So go to that link and give this a shot. By the way, so many of you watch this video and are not subscribed. So please consider subscribing if you wanted more content, more data, and more analysis. And so what I want to do first is use train test split to split up the data. I'm going to use a test size of 20%, a random state of 42, and then I'm going to set up my ridge model. Next, I'm going to take my training data. I'm also then going to take that fitted model and predict on my test set. And we're going to evaluate the model using the mean squared error and the R squared score. When we look at this really quickly, you can see that we have a mean squared error of 81 and an R squared of 0.9. So this is actually a pretty strong start. But recall, we've done no optimization. We've just chosen one parameter for alpha. And so later on in this video, we're going to optimize this model and see how much better it can be. We're going to visualize using this scatter plot here where we have our actual percent adulterated. So these are the ground truth, the true values on the x-axis, and the predicted percent adulterated on the y-axis. So the idea was that we would have a straight line along the y equals x line that I've shown in the dotted line here. And we can see that for some of the regions, we have a few samples that fall off in the low percent adulterated. So these would be our authentic samples. But we want to see if we can improve this linearity by correcting the model and using better hyperparameters in this case. And so this is where grid search CV will come in handy yet again. So in this case, the only parameter we're going to tune is this alpha parameter. And this is just a way to help us regularize the model, help us to deal with some of the covariation that we know will exist in this NIR data. Of course, there are several other types of models that might do better, but I'm going to stick with my ridge model. I'm going to optimize my alpha parameter using grid search CV, and I'm going to score it using R squared, and then run through the same process as before. When I run the cell, we will have a set of parameters. And we can see that the best parameter is an alpha of 0.1. We have a cross-validation now of 0.93, which is slightly better than before. We have an R squared of 0.94, which is better than our last test R squared value. And we've reduced our mean squared error from about 80 to close to 48. And so you can see just by tuning this one parameter and adding some regularization to our model, we've significantly improved the performance. And so let's create that scatter plot again so we can see how well it's doing. And now you can see we have a better fit into the lower percent adulterated region and continue to maintain pretty good fit in the higher, more adulterated part of our data set. So in this video, I've just demonstrated a way that we can take the model and everything we've learned previously to now understand how much our materials have been adulterated. In the next video, I want to combine the classification model and the regression model. I want to demonstrate how we can now build a multi-step process to allow us to first predict if we have an adulterated material, and if so, to trigger a regression analysis. I'll see you in the next video. Peace.